In this video, we are going to be exploring an example that's asking us to draw the total stress, pore pressure, and effective stress diagram for the soil sample subject to downward seepage. So to get started, let's go ahead and draw our given diagram. So far, we haven't actually started the solution yet. We're just going to draw a given diagram. So what we're given is a soil sample like this that is subject to an inflow of water at the top. So that means that we are going to have the case of downward seepage, and here's our water level up at the top. And then a little bit below that, we're going to have our soil sample. And then at the bottom of our soil sample, we're going to have, an outflow. And then as we've seen in the lab, we always have some kind of porous stone at the base of a sample, and usually also at the top of a sample. So in this sample, we're going to install 3 piezometers, okay? We're going to have one piezometer that is installed near the top of the soil sample. And in this piezometer, we're going to have a water level that is at the same level as the water level in the sample itself. So right there is our top water level, and we're going to say that this is installed at the top of the soil sample at point A. Then we're going to install a second piezometer at the middle of the sample, which is going to be right here. Now in this piezometer, the water level is going to be a bit lower. And again, in the case of downward seepage, that's what happens is when you have downward seepage, your piezometric head is decreasing as you go deeper into the sample. And then we're going to install a third piezometer at the base of the sample. And this will yet again be a lower water level. So if you take a look at the subsection in the textbook on downward seepage, there's a explanation on this. But for the case of downward seepage, your piezometric head gets lower as you go deeper below the top of the sample. So in the middle of the sample, we're going to have a point B here. And then at the base of the sample, we're going to have a point C that we're interested in. Now, let me go ahead and give you some dimension lines. The height of the water itself is going to be 1/2 foot above the soil sample. And then the soil sample itself has a total length of 2 feet, with point B being right in the middle. So we can put a 1 foot dimension line between points A and B, and another 1 foot dimension line between points B and C. And the soil sample itself has a gamma sat equal to 115 PCF. Now, let's talk about the dimension lines in the piezometers, okay? So the dimension line from the piezometer at point A to the water level in the piezometer at point C is going to be 3 inches right here, okay? And then I'm not going to directly give you the piezometric head difference between the piezometers in point A and point B, but we can end up calculating that here in just a second. We're going to say will calculate. Okay, so this is all of our given information. Now let's go ahead and tackle the solution to this problem. Again, we want to draw the total stress, pore pressure, and effective stress diagrams for the case of downward seepage. So under solution, what we need to do is we need to compute total stress, pore pressure, and effective stress at points A, B, and C. And we have to do this again because think about what the problem is asking for. It's asking us to draw the diagrams. So we need to generate the diagrams, we need these points that fully capture what's going on throughout the length of the specimen. So the first thing we should remember is that for downward seepage, for downward seepage. Total stress at an intermediate point is going to be equal to unit weight of water times the height, call it maybe H1, and then plus a saturated unit weight times some depth Z. And of course, you know, Z is measured from the top of the specimen down, okay? And what is pore pressure going to be calculated as? Well, pore pressure for the case of downward seepage is unit weight of water times, you know, height 1 plus gamma water times Z. And for a case of downward seepage, we have minus gamma water times a hydraulic gradient times depth Z. And then, of course, you know, effective stress is total stress minus pore pressure. Okay, so we can combine those together, and you know, you could algebraically combine these and end up with a gamma prime Z plus I Z gamma water. And I believe these formulas are summarized for you in the textbook for the case of downward seepage. So let's go through this one at a time. Let's look at point A first. So point A is at the top of the soil sample, and it's just directly under a this actually was supposed to be half a foot of water. Make sure you say 0.5 feet or 6 inches, half a foot of water. So here we go. Total stress at point A is going to be half a foot times 62.4 PCF. And of course, we get 31.2 PSF. The pore pressure at A is also half a foot of water. And so again, we get 31.2 PSF. And then obviously it's pretty clear the effective stress at A is 0. So that's easy enough. Now, what about that intermediate point B? What about that intermediate point B? Well, let's go one at a time. The total stress at B is going to be equal to the unit weight of water times, you know, the height of water plus what? Plus the gamma saturated, so the saturated unit weight of the soil, times the depth Z where point B is located. So we'll put that as Z right here. So how far below the ground, the soil surface is point B located? Well, it's located 1 foot below the top of the specimen. All right. So we can obviously say sigma B is 62.4 PCF times half a foot plus 115 PCF times 1 foot. And when we punch this through, we get 146.2 PSF. And let's go ahead and calculate the pore pressure at B. Now, this is where some things are a little bit more unique. We're going to have unit weight of water times the height of the water plus unit weight of water times depth Z minus unit weight of water times I times depth Z. So here's something that we have to be careful about. We need to pay attention to the piezometric head at point B. So this is where we're going to be interested in this thing that we said we'll calculate here earlier. So let's go ahead and substitute values in. So of course we have 62.4 PCF times 0.5 feet of water plus another 62.4 PCF times 1 foot of water. And then we're going to wrap this equation around and say minus 62.4 PCF times the hydraulic gradient. Remember, the hydraulic gradient, I, is for the entire specimen. So what's the hydraulic gradient for the entire specimen? Well, we're going to say that that's 3 inches divided by 24 inches. How do I know that? Well, again, look back at those piezometers. The hydraulic gradient for the entire specimen, that has to do with the head loss from the top of the specimen to the bottom of the specimen, which is point C, which that head loss is 3 inches, divided by the length of flow, which is this full 24 inches. So one thing we could write off to the side is we could say the hydraulic gradient for the entire specimen is 3 inches over 24 inches. All right, so that's where that's coming from. Now we then multiply that by the depth Z below the specimen surface, which is going to be 12 inches or 1 foot below the top of the surface of the specimen, which is point A. And then that's it. Now you may be wondering, do I need to convert these units, 3 inches, 24 inches, to feet? You can, but you don't have to, because hydraulic gradient is a slope. It's a ratio of length over length. So you could convert these both to feet, but it doesn't matter because you're converting both numbers to feet. So the units cancel, and you can clearly see here the inches cancel. So when you evaluate this, you get 85.8 PSF. Now punch this in your calculator on your own and convince yourself of it. And so of course the effective stress at B is total stress at B minus pore pressure at B. And so when we evaluate this, we get 60.4 PSF. Okay, now let's go to point C. Point C was at the bottom of the specimen. Point C is at the bottom of the specimen. So in a similar way, we're going to say the total stress at point C is we have half a foot of water. And then we're going to have another 2 feet of water, right? Because the whole specimen is saturated. That's a 2 foot long specimen times 115 PCF. So saturated unit weight. And we'll evaluate this as 261.2 PSF. And then we'll compute the pore pressure at that bottom point C. And we will end up writing 0.5 feet times 62.4 PCF plus another 2 feet of the water. So times 62.4 PCF here as well. And then we're going to say minus, and here comes the hydraulic gradient term, 3 inches over 24 inches. And next we will multiply by the depth of interest, which is point C, which is 2 feet below point A. So that'll be times 2 feet right here. And then, of course, times 62.4 PCF. And when we evaluate all of this, we should get a pore pressure value of 140.4 PSF. And then, of course, effective stress at point C is total stress at C minus pore pressure at C. And we'll end up with a value of 120.8 PSF. Now we are ready to generate these plots. So similar to what we have seen before, we can establish a depth axis. So I'm going to put 3 plots here, and I'm going to have 3 depth axes. So this is depth in feet. And I'm going to go ahead and establish my points. This is the top of the water here. Point A is going to be half a foot below that. And then, oh, didn't mean to jump like that. And then another foot below point A is going to be point B. And then another foot below point B is point C. So let's go ahead and label those points A, B, and C. And I'm going to call this first plot the total stress plot. And of course that has units of PSF. And we can go ahead and plot this out. Now on a homework assignment, you want to do your best to draw this to scale. So I'm not going to be the most artistic right now, but you want this to scale, and this will, ooh, that looks horrible. How about we just redo that segment? That's a little better. And then a little bit better there. So this is 146.2 and 261.2. And then that's the total stress plot. And then we can draw a similar plot for effective stress here. I'm sorry, not effective stress, pore pressure. So the pore pressure plot will have the following values: 31.2, and then we'll have 85.8, and then we'll have the 140.4, and then we'll have the effective stress plot. And when you have the effective stress plot, the top region of the water cancels itself out. So here's your 60.4 PSF, and then 120.8. And of course, you know, we should label these and make these look nice and neat. So here's total stress, here's pore pressure, here's effective stress, and we'll go ahead and label these things here: pore pressure, PSF, effective stress, PSF, and then we can put our Z labels here. So again, make these look nice and neat, draw them with a straight edge, and draw them to scale. But that's it in a nutshell. This concludes our example. One last comment. Make sure you're very careful. Notice that these slopes may change. So if a slope changes and you're drawing this to scale, you're going to have little kinks here. So take a look in the textbook and see where the slope changes. So you'll have a little kink in your plots at some of these points. So that needs to be reflected when you draw your plots to scale. So that'll conclude this video.